Then let's start the WIUCAS Biosoft Matter workshop 2023. And basically this is a workshop for Professor Debye Andelman. And I wanted to introduce the young people of this institute to Debye, and also Debye to young people, including Rudy.
The youngest.
Yeah. And let me first formally introduce you, David. And Professor Andelman is the professor of statistical physics at the School of Physics and Astronomy, Faculty of Exact Sciences, Tel Aviv University. He received his PhD in 1984 in physics from MIT, and then spent 1 year from 84 to 85 at Joliot-Curie Fellow at Collège de France in Paris under direction of Professor Debye. And then 2 years from 85 to 87, he was a postdoctoral fellow at Exxon Research Corporate Laboratories in New Jersey. And in 87, he joined the faculty of Tel Aviv University, and between 2011 and 2015, he served as the chairman of its School of Physics and Astronomy. And Professor Andelman uses theories and models for physics to study soft condensed matter and biological physics system at the molecular scale. In the recent years, his interests are devoted to the understanding of electrostatic effects in soft and biomatter, ionic solutions, charged polymer, and charged biomembranes. And another direction of research is dedicated to self-assemble of block of polymers, their patterns and application in nanolithography. And Professor Andelman served on the editorial boards of several journals, including European Physical Journal EPJE, Soft Matter, Soft Materials, and European Biophysical Journals. And he was rewarded several awards, including American Physical Society recipient of he's the fellow of the American Physical Society, and recipient of the Borg Award in 2003 from Royal Society of Chemistry, and Paris Sciences Chairs 2005 ESPCI, okay, and the Humboldt Prize 2002 Germany. And he was a Henry the Rothschild Fellow in 93 Curie Institute, and also Yamada Fellow 91 Japan, and the JSPS Fellow 97 and 2002. Okay. And and David, I met David actually maybe in 1991 in Japan, when it was the first visit to Japan, right? And he gave a seminar in Tokyo University, and I think we just happened to have some conversation because he wanted to copy something, and I just helped him copying. We had a very short conversation, and at that time he was staying with Professor Kawasaki in Kyushu. And actually later, maybe 1 or 2 months later, he sent me with his references and also a personal letter to me, and encouraging me to come to Europe and also Israel. But honestly speaking, at that time, I didn't know exactly where Israel is located. And then later, maybe in 96 or 97, we started to meet again, and then actually our collaboration started over the last maybe 25 years. And I also visited and stayed in Israel from 1999 to 2000 for 1 year. And although I don't want to make this workshop something personal, but I just want to show you 2 pictures. So this is the picture from 99 when our family went to Tel Aviv. and we were invited to David's family, okay? And so that is David, maybe 20, almost, this is 99, so 25 years ago, 25 years ago. This is me, this is my daughter.
Not 20.
Huh?
She's now 25.
She's now 25 already, yes. And so we have a very good memory from this time. Okay. This is basically David's family, and another picture that I chose is this one. Okay. So this was in Cambridge, perhaps 2004, yeah? When we were in the Newton Institute. And this is King's College, I think, yeah. And this is the picture that I took, okay? And you know, also another famous Chinese scientist, Professor Ouyang, okay? And we were together at that time. So this is exactly 20 years ago, and we stayed in this institute for maybe 1 month, and we had a very good experiences and interactions at that time. And of course, so David is for me like a scientific brother, and he taught me not only science but many other cultural things, including music and art, culture, foods, and so he really guided me into several new fields and made my life very rich. And also, one of the reasons that I'm now in China is also due to David. Basically, he suggested me to find a place also in abroad, not necessarily in Japan. And unfortunately, we didn't have time to directly meet during the last 4 years, obviously, because of the COVID. But I'm very happy that David could finally come to Wenzhou and see again here. So we spent several days from the last week, and unfortunately he will leave tomorrow. But today I want to have an interaction with David, also people in the institute. So thank you very much, David, for coming. Okay.
Thank you.
And, I want to switch to David's talk. So
Okay, so maybe
let me introduce you.
you want to
Just connect your computer.
okay.
So, and he will give the first talk of this workshop. Yeah. But his title is 100 Years of Electrified Interfaces, and what's new with the theories of Debye and Onsager.
Second,
Yes. By the way, today the ring will alarm you 5 minutes before your talk, and second ring, final talk, and third ring at the last of the session. Probably this is a Japanese system, which I want to try in China. Okay. If it's uncomfortable for you, just let me know. I just want to try.
Okay, so do I need to
keep it? Yeah.
Okay, so you know, when you hear such an introduction, you can conclude a few things. First of all, that I'm already pretty old, because you have all this history. But you know, besides all these details about all sorts of achievement or pseudo-achievement, I think that even now, you know, I'm not the oldest in this room, but I'm one of the oldest. Even now at my age, I think that I still remember why I started to learn physics. It was really the best thing that I did in my life. And it doesn't matter you are chairman, you are this, you are that, but if you are passionate about your work, and you know, I'm always saying that I'm so fortunate because I'm doing my hobby and I'm getting paid for it, you know. So, and it's really, this is something that we all have to remember, that, you know, to do research, to do what we are passionate about, this is the best gift that one can get in the world. The other thing is, when I started to do physics and I was a student and then PhD student at MIT, I also realized that physics is an international language. And I really tried a lot to use physics, and I visited and I collaborated with people in Brazil, in Argentina, in Mexico, in Japan, and you name it. Every place almost that there is physics, I was there. And besides the physics, of course, you communicate and you see other people and other structures, other type of cultures, and it's broadened a lot your horizons. And finally, the last thing that is very important in my age is to work with young people. And again, this is something that we are fortunate. People that retire usually, drink coffee with other retired people, but we are fortunate to have all the young people, the students, and they really rejuvenate us. They really, and so in this sense, I'm very fortunate. Okay, so that's the general thing, and let me start. So you see the talk is not a technical. Do you hear me okay? Because there is some noise. Okay. So the talk is not a technical talk. It's like an overview, and of course, it's things that we did in our group. And so it's about revisiting some of the old classical works of these great masters, Debye and Onsager. And mainly, I want to say a few things about Onsager. Professor Debye here also is a big admirer of Onsager. And I want to say a few things. Maybe you know Professor Debye, but maybe not. What I wanted to tell you is this story. There is a story. You see, it's almost 100 years ago. And the story is that Peter Debye, Professor Debye, your theory on electrolyte is incorrect. And Professor Debye, although he was a traditional type, he was Dutch, but like a traditional German professor, didn't throw the guy from his office. He asked him to sit down and to explain what's going on, why. And actually, this young guy was right. And not only that Professor Debye was convinced that the young guy is right and his paper is wrong, but he even offered him a position, an assistantship in the group for the year after. Now, of course, you could guess, or if you didn't know, that this guy was Onsager. So this is a picture of Onsager when he was young, maybe 17, when he was finishing high school. By the way, Onsager didn't have a PhD even at the time. He was from Norway, of course. And this is, of course, a more familiar picture. This is a picture that you can find in his Nobel website in '68. And, of course, 43 years later, Lars Onsager was awarded the Nobel Prize for what is now called the Onsager reciprocal relation, which even today is extremely important, especially for all the many people that are doing now out of equilibrium statistical mechanics and thermodynamics. If you want to read more about what I told you, you can look at this paper by Michael Fisher and his collaborator in Journal of Statistical Physics. Now, Lars Onsager probably, and I think I would even say without probably, he was the greatest statistical physicist of the 20th century. Okay, we all know the great master of the 19th century, Gibbs and Maxwell and many others that established, Boltzmann of course, that established the principle of thermodynamics and statistical physics in mechanics in the 19th century, but Onsager did so much, and he was awarded the Nobel Prize on work that he did in the 30s, this reciprocal relation, but he did two other things that each of them probably would merit a Nobel by itself. One is what he actually solved single-handed the two-dimensional Ising model in the late 40s. He showed that critical behavior is not an approximation, but the singularity really exists in the thermodynamical limit. You have some exponent, the critical exponent, and this was one of the first times that you would really solve a model that is non-trivial, not a one-dimensional model. The other thing that he did more or less at the same time was that, again, he showed that the isotropic kinematic transition in liquid crystal is again not a smooth transition, but it's a really sharp transition that happened in this limit that he took of very long molecules. So each of these work is a really tour de force, a masterpiece that he did, and of course he had many other contributions. And one thing that goes throughout his career is that he was always, beside his other work, he was always thinking about electrolyte and ion solution from the beginning. When he came to in 25 to Debye and told him that the theory was incorrect, I will comment more about that later, till more or less the end of his career in the 60s. And he also worked on many other things, including order in ice and water, and the electric and turbulence, and many other things. If you want to read about all his work, you can look at this collected work. There are about 95 publications, it's not so much today's standard, but there are many works that are really gems, and also this article by Michael Fisher, if I'm not mistaken, it's the first chapter in this. Okay, so that's about his life. He died in 76. I also have another anecdote to tell you. So Onsager worked in Yale University, which is in New Haven, in Connecticut, in the United States. And he died in 76, he was maybe 73 or so, and he was very close to Kirkwood. See, this is the tomb of Kirkwood. Kirkwood was another rather famous physical chemist in Yale. Actually, Kirkwood was one of the people who brought Onsager to Yale. And so this is the gravestone. You see the Kirkwood gravestone is very, very big. It doesn't work so well. Yeah. So Kirkwood, you see, it's very big and a lot of details. Onsager is smaller and very few details. If you look on closer look, of course, this is not Kirkwood and not Onsager did that. This was the wife. But Kirkwood's wife really wrote his whole CV, even longer than what you were telling me. And he was a famous guy, so he had many awards and chairman and this and that. So all of this is inscribed here. For Onsager, so you see 1903, 1976, born, died, and so on, and just Nobel laureate, and that's it. It's enough. Now, when his wife was quite a character also, Margaret, when his wife died about 20 years after, in 91, then the children, you see that the Nobel laureate had a little star. And this star was added by the children, and if you look a little bit down, the little star goes, etc. Nobel Prize, star, etc. Because, you know, if you look on the award and of Onsager, the list is much longer than Kirkwood, but this was their way of showing this in an indirect way. Okay, so this is sort of my introduction and in general I think about Onsager. He was really a quite a character. I mean, there are many stories about him.
Wife. Do you know? How do you know Onsager's wife?
How do I know that she did it?
Yeah. Well, no. Yeah. I mean, so that you said that she's a character.
That he was a character?
Have you met her? No. Maybe not.
No, I didn't meet her. No. How do I know that she was a character? I mean, this was, you know, in what is written. You look in Wikipedia. She was Austrian, and yeah. So she was, and the children also talked about that. You can find in Wikipedia many of the, I mean, the detail like this one, you find it. I didn't invent it. But yes, she was. So there are many stories about Onsager. I mean, you know, he was giving seminar. It was catastrophe. Courses nobody understood, but of course he was a real genius, and I think everybody agrees. Okay, so given the limited time, so this is my outline. So I will start by making an introduction to the Poisson-Boltzmann theory. I will not talk about the electric property just because of lack of time, but you see that Onsager's name is related, also Kirkwood is related to this. I will talk about two different topics. One is surface tension of electrolyte, which is based on the famous work of Onsager together with some others from the 30s. And the other one is actually the work where Onsager corrected the work of Debye and Onsager, and this is the work that is related to what I mentioned in the beginning, that he said that something was wrong in Debye, and indeed it was wrong. Okay, so before I continue, I would like to acknowledge my collaborators, so that these three were my students, they all graduated. Tomer Markovich was a postdoc at University of Cambridge and Rice with Mike Hayes and McIntosh, and now he's a professor in our engineering faculty. Ramadar was followed me to Collège de France, and now he's a faculty member of the Technion, the Israeli Institute of Technology. And Yael Avni was my last student, and she's now a postdoc at Chicago with Vitelli. And this guy here, maybe you can recognize, although you didn't have the beard, this Chinese type of beard. So he's, yeah, so I know Rudy for 30 years. 30, a little bit, maybe. 30 years, and he's older than me with 1 month. Okay? So he's my older brother. And of course he's working now in Beijing. And Henri Orland is even an older friend and associate. Actually, when I was a student at MIT, he came as a young professor. He gave a course that was 40 years ago. And we continue our collaboration all the way. So Rudy and Henri were very instrumental, together with my student, to do the work that I'm going to present. Okay, so let me first start by some very general motivation. Maybe in this room it's not so important because you are well familiar with electrostatics, and what I say is that, you know, the most important and special liquid on Earth between 0 and 100 degrees Celsius is water. So some people say water is a universal solvent because you can solubilize so many things in water, ions and other substances and organic material and inorganic material. And life is basically based on water. Life was established in the oceans where you have water and electrolytes, and this is why, you know, every living organism on Earth has, you know, the majority, the most abundant component in our body is water, and everything should work in water. So if you look in biology, yes, so you have simple ions like salt that are essential electrolyte in the blood, in the cell, in the trafficking of substance from the extracellular to inside the cell. You have membrane of each cell that is composed also of charge, component charge phospholipid. You have macromolecules, biological macromolecules like RNA, DNA, protein, polysaccharide, they are all charged. So definitely electrostatics, because of the water and the solubilization of ion in water, is essential to life. If you look in chemistry, in our charge, or at least our polar, or can have some charge that will dissociate or associate. In terms of the statistical mechanics of charge system, this is a big headache, and there is no real formal closed solution to this problem. The problem is that, you see, you can envision some model system. You see this is water. Water, of course, is not a passive medium, but it's molecules by themselves, which are highly polar. You have small ions that move around because kT is essentially an important room temperature. kT is comparable to any other energy of any other degree of freedom. And then you have maybe some macro object like colloids or some interfaces where you have some charge distribution, and the system is all the time reacting. The small ions are affecting the distribution, but they are also affected by the distribution of all the other charges. So you have this, you have entropy, you have the water, you have long-range interaction of the electrostatic interaction, you have screening, and all this together is not a problem that can be solved exactly. But you can do, of course, simulation, and you can try to do some simple analytical approximation in order to understand what is the essential ingredient. So, Poisson-Boltzmann, of course, called after the two great masters of physics and mathematics of the 19th century. So, Simon Denis Poisson, you know him, he did many things, among others the Poisson equation in electrostatic. So he worked in France, in Paris, and of course Ludwig Boltzmann, he was Austrian, and he basically the father of the statistical mechanics. And although we call the theory Poisson-Boltzmann, you see that Poisson died 4 years before Boltzmann was born, so it's not that they had some French Franco-Austrian collaboration, but we call this theory like this because it has ingredient of the Poisson equation and of the Boltzmann distribution of statistical mechanics. So what is the Poisson-Boltzmann equation? I'm sure that most of you know this, but let me reiterate. You have the, you start with some approximation. First of all, I will do it only for mobile ions which are monovalent, 1,1, and the density, the local density of the ion depends on the Boltzmann weight factor, where for energy I take only the electrostatic energy, E psi, times the charge, where psi is the electric potential, the local electric potential that is felt by the ion, where you see the mean field of all the ion around it. I'm not taking the Coulombic interaction between any two, I'm taking some average, and this is already by itself an approximation. So you see that the local charge distribution will depend on this factor, where psi is also local. And then Poisson equation that always holds in electrostatic just tell you that the Laplacian of psi is equal, proportional to the charge distribution, local charge distribution, and this, in this case, is n is the number density, and this is because the charge of the minus is minus, so this is why you have here a negative sign. So if I plug in the first equation into the second, I get this rather simple second order partial differential equation, which is nonlinear. So the Laplacian is proportional to the sign, hyperbolic sign of the potential. So this is one equation for one unknown. For psi, you know psi, you know also n from here. And basically everything now depends on the boundary condition. So you can solve this equation given boundary condition. This is a mean field approach for the density of ion and electric potential. The boundary condition can be either constant potential, what is known in differential equation to be Dirichlet boundary condition, or the charge is known, charge is related to the electric field, the derivative, the first derivative of the potential, and this is a Neumann boundary condition. And of course, we have also other type of boundary condition, and this comes under the word, the term of charge regulation. I'm not going to say anything more about this because this is exactly the title of Rudy. And there was a lot of work. Rudy basically initiated this type of work, and I also participated in some of the stages. So this is some type of more complex and more realistic boundary condition where you don't have a constant charge and not constant potential, something in between, but in many physical systems or biological systems, it's more realistic than the other two. Okay, so what do? You have a nonlinear partial differential equation, and let's say in biology you have very complex boundary condition. So you can do one of two things. Either you go to this website, Poisson-Boltzmann.org, and there are many other. I think this picture was not taken from this site, but there are many either freeware or something that you pay, you get some software, and if you don't worry about the physics and the math, you just put in all the charges, the electric constant and everything, and you get the solution of the Poisson-Boltzmann equation, you get the distribution of the ion, you get maybe the energy that one ion, let's say a protein approach a membrane, and you get what is the energy and things like that. But this is not our way of doing things. What we do things is we try to do very simple models where we extract the essential physical parameter. And this physical parameter comes you can look at it in different ways, but I will emphasize some length. So Debye and Onsager, before the work that they did, that Onsager also later on corrected, there is a very famous work from 1923. I think there are two papers that they wrote, and this is setting the foundation of the modern theory of electrolyte, where basically what they observed, what they concluded, is what we call today the Debye screening length. The Debye screening length means that when you have both positive and negative ion in solution and they are mobile, each ion, like you can see here, I just picked randomly one of them, the last one, each ion will be surrounded by a cloud of mobile ions of fluctuating plus and minus. And this cloud is screening the electrostatic interaction between any ion and another ion. And you need to do it in some self-consistent way. The characteristic length of this screening, meaning that outside this cloud there will be very little interaction between this ion and another one, is noted lambda d, d for Debye, and you can very easily find it also by linearizing the Poisson-Boltzmann equation. And you see the coefficient here, which has units of 1 over length squared, is exactly the Debye length. And the Debye length depends on the density of the ions, on their charge, the electric constant of water, thermal energy. But instead of looking at this, you can just remember this simple thing. The Debye length is 3 Angstrom for 1 molar of salt, and it depends as 1 over the square root of the density of salt if you have different molarity. Of course, this is only for water, epsilon is over 80, and room temperature, it's already inside, and monovalent type. If you other thing, then you have to change it. So you see that 1 molar of salt is a lot of salt. For NaCl, about 6 molar in saturation, the salt will crystallize. And 1 molar is a lot of salt, and then the Debye length is very short, like a size of a water molecule. And this means that after, if you do 3, 4, 5 times the Debye length, the electrostatic will be basically screened. If you have less salt, then you can go all the way to this artificial limit of pure water, where you have 10 to the minus 7 molar of the association-dissociation of the hydrogen and the OH. Then you get 1 micron, but of course this is not realistic, because you never have really pure water. And realistically, you can speak about between few angstrom or a fraction of a nanometer, all the way to maybe tens, 50 nanometers, something like that, 500 angstrom. And there is another length which is important, and you will see it in my talk. This length is a Bjorn length. It's just basically, you see this combination of constant, and at room temperature is about 7 angstrom in water. This length is basically, you take two charges that interact between themselves electrostatically, and you ask when the interaction between 2 charges in water equal to the thermal energy. And this is exactly 7 angstrom. Of course, if epsilon is not 80, but it's 1, like in vacuum, will be much bigger. And then, you know, it's easy to express lambda in terms of the Bjorn-Lang, because then it's, all the other coefficients are absorbed inside the Bjorn-Lang. And Bjorn was another important scientist 100 years ago. Okay, so this is my introduction, and now I want to tell you two stories. The first one, Rudy was involved. In the second one, Henri Orland was involved. The first story is about looking again at surface tension of electrolytes. And as I said, this is also going under the name of Onsager, who worked together with a collaborator, Samaras, and they wrote a paper, I think in 1934. And the paper is about how the salt, you solubilize, how would the surface tension of salty water, like ocean water, sea water, will be different than the surface tension of pure water, like this one. The surface temperature, it's about 70, 72 Dynameters per centimeter, or millinewton per meter. And I'm now talking only about not this 70 of water, but how is the surface tension of water change? How does it change when I introduce salt? So only about this part, okay? Because for water, I don't have a theory, and in our work also in Onsager work, water was taken as a pure passive media, and the surface tension of water was given. So I'm only looking at the increment of the surface tension. So imagine that you have water, epsilon is 80, it's a continuum media, no structure, and there is an interface here which has no charges on it. It's completely neutral. And on the other side you have air, or you can have oil or some other media with a much lower dielectric constant. For air, of course, it's 1. And now I put, so first of all, what I want to say, and this is something that Rudy already mentioned in his PhD thesis many years ago, is that if you look on the Poisson-Boltzmann of this problem, you will get nothing. Because if you don't have any charges on the interface, you will get that there is nothing, you are averaging laterally, so there will be, even if you have salt inside, there will be nothing, because the Poisson-Boltzmann depend on the boundary condition, and there is no charge there, then there will be nothing. It will be just a bulk with another bulk. So clearly that Onsager, even 19 years ago, when he had his idea, he didn't phrase it this way because they didn't think about it in terms of mean field and fluctuation, but his idea was already going beyond mean field, and this is really beautiful. Not everything that he did was original. Some of the ideas were known also in the 20s before him, but definitely what he did was a very strong leap forward in solving this problem. So imagine that you have this dielectric discontinuity between the two media, and I just take one ion. Doesn't matter positive or negative, I put it in the water close to the interface. Now we all know from freshman physics, we all know that if I take an ion, instead of solving now the boundary condition, which is this dielectric jump, I can use the image charges I can use this trick of image charges and forget about this boundary. I just put another ion, and this ion will have a negative sign when this has a negative sign, because this ion is in the high dielectric constant. If it would be on the opposite, it will have an opposite sign. But if I put ion from the high, the image charge will have it's a very simple exercise that anyone can do. And of course, if you have now a real ion interacting with this image, and the two ions have the same charge, this means that there is a repulsion, because it's minus with minus or plus with plus. So if you have a repulsion, this the Duncan experiment tells us that ions do not like to come to the interface, they like to be away from the interface. provided that they are embedded in the high dielectric constant. And you can understand that because the ion here has some electric field, and if you take it close to the interface, you are, because you need to satisfy this boundary condition, you are perturbing the force line of the electric field, and it prefers to be inside the solution where it can be surrounded and not affected by the interface. So, if you indeed have this repulsive interaction, this means that the density of ions, just because of this dielectric constant jump, will be less at the interface than inside the bulk. So if you have some solute that has less density close to the interface, it means that the surface tension will go up. This is exactly opposite than surfactants. Surfactants are amplified, they like the interface of water and oil, or water and air, and they reduce the surface, like so, they reduce the surface tension. But in this case, you have a depletion of the ions, and the surface tension is increased. So this is one of the ideas that Onsager had. I'm not going now to show you the details. You can, for example, read a simplified version in Lambda and Lifshitz, in the books of Lambda and Lifshitz on StatMech. And what they did is they took this interaction, this repulsive interaction of the ion with the image or with the interface, and they embedded this ion, because there is not only one, they embedded it with a solution of all other ions. And this was the new thing of Onsager, and they basically used the Debye theory of electrolyte, but with this additional repulsive interaction at the interface, and they did it, and they calculated the extra surface tension, and the extra surface tension that they calculated was very simple. It was, the scale was kT, and then it was something that goes as n log n. N log n. N is the concentration of the electrolyte in the solution. Now, and you remember that n, the density, goes like 1 over the Debye length squared. Now, you see that in this simple argument, there is nothing beside the charge, which of course if it divalent it will be a little different because the Debye length is different, but there was nothing beside that that tells us anything about ion specificity. And we know that it's not so simple because the different ion will act differently. Also, you see that it's the same if I take a negative ion or a positive ion. The argument is, on one hand, very simple and elegant. On the other hand, it doesn't retain a lot of the physics. Okay, so these are experiments. So you see that these different lines, I mean, the lines are fixed, but the different dots, you see, it's an experiment where the cation was always sodium in this case, and then an homologous series of fluorine, bromine, iodine, and you can. So it was known that different ions will have different effect on physical, chemical, and biological properties in a very consistent way. It always goes hand in hand. And one of the manifestations is the surface tension. So we tried, together with Rudy and with my student at the time, Tomer Markovic, we tried to address this question. So I'm not going to show you the detail, just the essence of what we did. So what we did was we used a phenomenological parameter, we call it adhesivity. Adhesivity was a way to separate different type of ion beside the charge, beside this interaction of any charge in the interface. And it was a parameter. You can calculate this parameter from, for example, things like you know, what is the radius of the ion and how the hydration shell of the ion is arranged around it. We didn't do it, we just had a parameter alpha units of kT, and then we calculated within a self-consistent field theory, we calculated what is the effect of ions on the surface tension. And it was analytical within, of course, some approximation. And we got basically two terms in this extra surface tension. It was one loop expansion in this self-consistent field theory, so first correction to mean field. I want to say that mean field in this problem is very small because you do not have any average charge of the interface, so lots to do with the fluctuation. If you look, for example, on surfactants that are absorbed on the interface, charged surfactant like SDS, then this effect is much smaller, it's few percent. But if you don't have anything, this is a strong effect. And this is the result. And the result is, you see, is very simple. This term is exactly Onsager-Samaras term. You see, it's n log n coming from this Debye length to the minus 2. This is proportional to n. This is ln of lambda d is like ln n. There is some cutoff that you need to use. We took it as A, some lower cutoff, which is in some sense telling you the cutoff of a continuum theory. Otherwise, things have to diverge. It's like the size of the molecule. And so you see, this is exactly the Debye term. This term here is the electric difference between epsilon of water and 1, which is epsilon of air. And then there is this other term that is ion specific. Why is it ion specific? Because it depends on alpha. And sigma E is somehow like an effective surface charge that you get even if you don't have the charge on the surface. You have the ion that have a whole distribution, and the cation and the ion will have different distribution. And this is an effective charge, and for simple ion, this effective charge is small. How does it look? So what I showed before, this is exactly our fit to the experiment. So this is our fits where we have basically alpha as a fitting parameter. So we do have an alpha as a fitting parameter, but the sequence of alpha is exactly goes with like the sequence of the Hofmeister series. And this alpha, you see, is like a fraction of kT, 0.1, 0.2 kT, can go to 0.01 kT, something like that. It's a small fraction because these are very simple ions that do not have a strong affinity to the surface. Okay, so this was the first thing that I wanted to say, and in the time that I'm left, I will tell you the second story, the story of conductivity of concentrated ionic solution. And this is a story where we built upon the Onsager-Debye theory of conductivity, the same thing that appeared that I mentioned in the beginning of my talk. So, conductivity of ionic solution. So you have an ionic solution, very simple, let's say NaCl, take a salt, monovalent ion. You put two electrodes, connect them with a battery, and you have flow. You have, let's say, you have constant flow. And of course, the two types of ion will flow in this pictorial representation. The positive ion will flow to the right, and the negative to the left. And you have these two currents. Of course, you have to add up the two currents together. And the conductivity is basically the average of the two currents divided by the electric field. And if usually you want to do, you take it without a strong electric field, so you take the limit that the electric field is going to 0, and then you get a number. This conductivity is basically a number that depends on the concentration of the electrolyte and maybe temperature and many other effects, but doesn't depend on the electric field, because this is this linear response assumption that the current is proportional to E0, and then the ratio is not depending on the electric field. So the first thing is the dilute limit. The dilute limit was known also in the 19th century. This is a limit where each ion is flowing without seeing any other ions. So the positive one flows to the right, the negative to the left. You have the mobility of the ion, you take the average of the mobility, multiply by the charge square, and this is the conductivity up to this factor 2 because I have the average. So you see that the conductivity here is basically you sum all the ions because they don't see each other, and of course it will be depending on linearly on the number of ions, the density of ions. So this is well known. And then here comes the theory of Debye and the correction of Onsager. What they did is okay, so this is the kappa 0 is the dilute limit. Now you want to look at increasing the density in such a way that the ions start to feel each other. What does it mean that they start to feel each other? Imagine that you have this ion here that is flowing to the right and the negative ion flowing to the left. And when they flow, and they are close by, and of course being close by meaning that when you have more and more ions, there will be more incident of being close by. When they are close by, they will start to attract each other. So when they start to attract each other, they slow down their flow. And without any calculation, I think it's easy to be convinced that the conductivity will be less than the conductivity that you take proportional to n. So proportionally to n, the dilute limit always exists, but there is a correction, negative correction, that has to do with the fact that the ions attract each other when they flow, and they will take more time till they are into the electron. So this was in the theory of Debye. There are two terms. One term is a direct electrostatic term, which I expressed here not as they did, but expressed it as a ratio between the Bjorn and the Debye length. And the other term is hydrodynamically mediated, because you see each ion flows and then there is a solvent that flows around it, and then the two clouds of solvent that they come, they also interact. So it will also depend on not on the size of the ion, but on the hydrodynamic radius, which is this RS, the reduced stock radius that depend on the viscosity. So this term here, you see, depend on the ratio between the hydrodynamic radius and lambda d. So kappa 0, remember, this is the dilute limit. It by itself not a constant. It depends linearly on n. And then there are correction, and lambda d of course depend on n. So there are correction. Both of them are negative, and they depend on they correct down the conductivity at finite ends. How does the experiment look? So this is experiment in the very dilute limit. You see up to 0.1 molar or 10 millimolar, and you see that this is the curve. So basically no fit parameter, the curve of Onsager, Debye and these are data points. And the reduction is 5%, 10% for this very dilute limit. But if you now look at much more concentrated limit, you see that there is a big deviation, and you cannot fix it within the theory because there are no free parameters. So you see that all this area is concentrated here where the theory works, but then there is a big deviation. So something is missing, and people, I'm not going now to tell you the history of this was done many years ago, but people try to do all sorts of things to correct this, liquid theory, simulation, and actually they managed to do that. What you can see from here is that the correction is too much, which means that the ions do not have any size and they can approach each other very closely and spend a lot of time because they are attracting each other. So something tells us that for more concentrated solution, you cannot have this incident that the ions are so close one to another, the oppositely charged ion. And you need to take into account the finite size of the ion. So this was somehow our motivation. So I think time is more or less. It's okay. So so what we did is so this is together with my student Yael and Ram and Riolan. So what we did is we were inspired by old work by Kawasaki and also by David D, who devised what he called the stochastic density functional theory. I'm not going to go into the details, but basically you see this is the current here of this electrolyte. You have advection, U is the velocity of the. You have this type of current which is stochastic, and this is, you get it by taking Langevin equation and processing it and going into this continuum limit. And they themselves, Dean and with his student at the time, Demery and some other people, they were able to reproduce within this stochastic density functional theory, they were able to reproduce the Onsager result. But they did not take into account the finite size of the ion, and this is something that we did. Now, to take into account the size of the ion like a hard wall is extremely difficult in field theory, so we need to do something else. So what we did is we modified the electrostatic potential in such a way that it has the reminiscent of the size, but at the side of the ion, when the two ions come closer, we don't take the interaction to be infinite, but we saturate it. So the theory is approximative because there is a possibility that the ion will interpenetrate to some extent, but we calculated all sort of average two-point correlation, and we saw that this is quite a good approximation. Of course, not for extremely concentrated solution, but in some intermediate range. So these are the ingredients that go into the theory. This is the flux with this new stochastic current. You have the continuity equation and compressibility, and of course Stokes law, and we take this modified electrostatic potential, and everything is linearized. So we go to Fourier space, we solve it there, calculate the current, go back to real space and calculate the conductivity. So after doing all this work, what we were able to obtain is we were able to obtain very simple and elegant analytical expression for the two corrections to the conductivity, the hydrodynamical moderated one and the electrostatic one. And you see that this correction basically depends on the ratio between this A, in some sense the size of the ion, and lambda d. And of course in the hydrodynamic one, it also depends on the Stokes radius. So very simple and elegant, just have to do this integral, or if you do not want to do the integral, you can expand in powers of A over lambda d, and this is the first correction in this expansion. Remember that A goes to 0 should give us back the Onsager Debye theory. And indeed it does, because if you take in this, you take this thing and take A to 0, you get exactly the first term of correction of Onsager, and if you take here A goes to 0, you get the second. So we are able to reproduce exactly the Onsager Debye result, and we have a very simple correction which depends on only, you can even say that there is no field parameter because we can take the size to be the size of the ion. And how does it look? So you see, this is how it looks. So this is NaCl and quite concentrated solution. This is the Debye-Onsager fit, and this is ours where the blue and the purple lines are whether we take the fully integral or we take this expansion. Both of them work quite well. And what is amazing and surprising is that with no fit parameter where we take the size to be the average between Na and Cl, the size of the crystallographic size of the molecule, we get a very good fit all the way to very concentrated solution of 3 molar. Of course, if I go after, it will deviate. But we were by ourselves very much surprised that the fit works so well up to beyond 1 and 2 molar. If you go to divalent ion, it will stop more or less here. Okay. But this is quite nice. And also we did fits with temperature, and again you can see the Onsager versus our, and again it's working nicely. Okay, so I think I'm a bit over time, so let me just summarize. We tried, we didn't do it on purpose, but this was somehow my way of working with Rudy and with Henry, and we touch upon different classical work with Onsager. I didn't tell you about this, but there is also some interesting way that we calculated the electric constant, the electric decrement of electrolytes. I didn't have time to explain that. You saw how we put ionic specific effects at interfaces and corrected the work of Onsager and Samaras in very simple and elegant terms. Of course, as I said before, there are many other works, simulation and some other theory, but what is nice here is that you can get the Onsager-Samaras work, but and also some simple correction that we understand. And finally, about the conductivity, the same thing. We use a theory where we reproduce the Onsager-Debye result for no size of the ion, and then we found correction with very nice fits to the theory. Okay, so I will end here. This is the end of my story. Thank you very much for inviting me. My first time, but I hope not my last time visiting Wenzhou. Okay.
Thank you very much. Very historical and also modern aspect of the electric systems. Thank you very much. So, there any questions? Please maybe put your microphone, use the microphone. You have to press the button on the right hand side. The microphone.
Yeah, thank you very much, and that's very interesting. So then when the Onsager visits and the device room, and so he objected this and that theory. What's wrong with the device?
What was wrong with it?
Yeah.
It's another interesting story. You can, I mean, I read about it in the article of Michael Fisher. He explained it. So what happened was that I think, and this is what people say, this was the beginning of Onsager thinking of the reciprocal relation, because in the theory of Debye, what happened, they were not consistent. They took one ion that is flowing ballistically and the cloud that is diffusing. And he told them, no, it cannot be, because every ion in the cloud is also flowing. So there was this inconsistency, and he solved it in a similar way that one has this reciprocal relation. So I have to admit, I never really looked at what they did. Everybody is showing this, he wrote 2 papers in 27, I think 26, 27, where he corrected what they did. So I cannot tell you that I know exactly, but the equation that I shown, this is already his correction. So this is consistent.
Or so that's a very famous theory of Andelman. So this is so there is always in a direct limit. It's kappa is some conductivity. Ions. No, kappa is an actual.
I cannot hear. I'm sorry. Can you speak with the microphone?
Oh. So kappa is an conductivity, or
yes.
Conductivity divided by the ion is kappa.
Oh, you are asking about whether
definition
kappa 0 by itself depend on n.
So it's
already n inside.
N is in.
Yeah, here, look. this kappa 0, you see here?
Yeah.
So this is kappa 0.
Oh, kappa 0, yeah.
So this was well known. You know, this is nothing.
Yeah.
It's just,
So
just every ion contributes.
Yeah, Onsager pointed out that this term needs to be corrected.
Yes. So they did correct it. Their effect is correct. Is very nice. It's not this dilute limit. Let's say because you start to get the interaction,
Okay.
but it's too much. You know, because this ion do not have size, they will spend too much time together because they can attract each other very much at very short distances, and this is why the reduction was too much compared to experiment.
So my question is about this conductivity, and you show some Stokes equation, briefly.
Yes, but only within the Stokes limit. Yeah.
So
No.
So this under electric field, ion feels some force, right? So I just want to see.
Yeah, just a second.
Yeah. So fluid mechanics. Yeah. Okay. Okay. I see. So body force, right? So in Stokes equation, the
inertia
force is like a kind of body force.
Electrostatic.
Electrostatic force is like a body force in Stokes equation. And both, but they are opposite directions. So essentially, in average, there is no net force. I mean, positive direction or negative direction.
You mean on the this is a directed flux, yeah. So
yeah.
directed flux. So the you know so of course they flow in opposite direction, but yes, in terms of the number, you are accumulating the ion in both electrodes, and
so
they add up.
Because of the density,
It goes at E square. You see, I mean the kappa. See, kappa goes at E square, so it doesn't depend on the sign of E.
Oh, okay. Yes. But
Because you know,
my question is about flow field. So if we solve this Stokes equation, we may have some velocity field.
yeah, this is the velocity of the solvent.
Exactly. So we do expect some kind of length scale of flow pattern or something. I mean, in bulk, if you put electric field, one is called that, one is called that. So there's kind of a flow field up here. I mean, if we solve this, but for some length scale, maybe the ion distribution is almost uniform, so we don't see any local flow field.
I understand, but it adds up. So indeed you have, see the question is what are you looking? Are you looking at current? See the particle is flowing in this way, but it carries a negative charge. So a negative charge goes in this way, and the positive, if both of them will go the same way, then of course they will cancel.
Yes.
But negative goes this way, so it's a vector, and the sign, the charge is another sign.
Yes.
So it's negative of negative and positive of positive, and they add up. You know, physically they add up, yeah, because in a battery,
But
yeah.
in the end, the solvent has no net flow.
So the solvent here is just, you know, dragging. It's passive, and it's just dragging with it, and it's not important unless the ions are coming close by and then they interact.
I want to conducted.
Yeah, of course there are many other effects where.
So do you have some numerical simulation of flow field?
We did you know, this I cannot say even that this is not a cartoon. These are really this one.
No.
This we did it. I mean, this is not cartoon, but this is very simple. Just
But this is very small length scale.
yeah, it's not like we don't do the whole system. Only two of them, and how the flow field goes between the two of them. There are people who are simulating I'm not sure in the simulation whether they took the, this explicit solvent type of simulation. In this context.
Last question.
No, I want to ask this. This is a very important question. Okay, the question is that what you are drawing here is some small scale. Macroscopically, if we have this situation, will the water flows or not is a question.
Of course.
And then what's the answer? I think that.
No, I mean not within our theory.
Yeah,
we don't have that.
Reality, experimentally, and what happened.
So this is the limit where you really take the field to be zero. So you hope that in this limit of linear response, this will not be an effect. But obviously, if you look on large field, external field, then you will you get all this.
So what Onsager did is some correlation effect, as you said, correlation effect.
Yeah.
But the macroscopic average velocity is zero, or I don't know. Okay. So I have some people talking about the flow. There's actually flow induced. But
Yeah, I don't have a good answer right now. I don't know in terms of. It's not in our theory as well. I mean, so we corrected it locally.
I thought that it will never move, but then recently I heard that.
Probably, definitely in this very low electric field. How can it move? It will not accumulate, and it will start to do convection around, or somehow it has to be average. Yeah. But it's not within our theory.
Okay, so I think time is running. So let's thank David again. Thank you very much. And let's start our next session from 10:30. So we will take 15 minutes break. 10:30.